Hello everyone, I will tell you about VLANs in this lesson. Let's take a brief look at our topics. VLAN concept, VLAN trunking, VLAN tagging, data forwarding between VLANs, VLAN configuration and verification, VLAN trunking configuration, data and voice VLANs will tell you. Virtual local area networks serve to divide our networks. Imagine you have 1,000 users and you use all of these 1,000 users when there are no VLANs on a network and you have a large broadcast domain, and when you send a broadcast packet on this network, these broadcast packets are delivered to all the users, or you want to set up an RAN-D network, you want to do an accounting, you want to separate their networks. Before there were VLANs, you were splitting your networks using separate physical devices for each of your departments, i.e. for accounting, for sales, so that you could do this. Now as you can see in this way, the users here are on a separate network, the users here are on a separate network, the users here are in broadcast domain 1 and the users here are in broadcast domain 2. A different subnet is used here, a different subnet is used here. Here we have divided the network without VLANs using a physical device, but now our switches have VLAN capability. This VLAN feature serves to divide our networks and separate our users on a single device. Think about RAN-D, users in RAN-D, users here are accounting users. We don't want accounting users to have access to RAN-D, we don't want users in RAN-D to have access to other users, and we're dividing these networks. Let's say that the users here can access the users here. But since there are many users in our network, we reduce the traffic in our network by dividing the broadcast domains. We can use it for this, or we can use it to prevent users from accessing each other, or we have different devices, we use IP cameras, we use IPTV, we have access points, and we can shape our network by taking them all into separate VLANs. But if there were no VLANs, we would have to use separate physical devices for all of them, but now we can logically divide them on the switch. Our users here cannot access here, our users here cannot access here, they cannot access it, but they cannot access it until we want to. If we want these users to access here, we need a layer 3 device, that is, a router, or this switch needs to have a layer 3 feature, then we can do data forwarding through routing, but there is no communication between VLANs in the default. We can give users the IP of the default router and give the users access to other networks through the default router. Let's look at using VLAN trunking on multiple switches on this page as well. Let's first look at our non-VLAN trunking structure. In this way we have two VLANs, VLAN 10 and VLAN 20. There's switch 1 and switch 2, and both of these switches have VLAN 10 and VLAN 20. VLAN 10 users on switch 1 need to be able to communicate with VLAN 10 users on switch 2, in the same way that VLAN 20 users need to be able to access each other. What do we need to do to ensure this communication? We take a port of the switch here to VLAN 10, we take a port of the switch here to VLAN 10 and connect the two ports together. In the same way, we make the port here and the port here VLAN 20 and the users on this switch access the users on this switch, but imagine that there are 10 VLANs on our switch. Are we going to pull cables for each VLAN separately? No, we will not, we will use VLAN trunking. When you use VLAN trunking, we add VLAN information to our Ethernet frames and send these frames to the other switch. When VLAN 10 users here need to access VLAN 10 users here, we put the port between these two switches in trunk mode. We have two modes in our ports, access mode and trunk mode. When we set these modes, we take the end users to access mode. If we connect the switches together and you want to generate more than one VLAN traffic on this connection, you take that port to trunk mode. Here a user in VLAN 10 creates his Ethernet frame when he wants to access a user here in VLAN 10 and adds VLAN 10 information to the beginning of the packet to indicate that he is also in VLAN 10, and since our connection is also trunk, he can pass multiple VLANs. VLAN 10 information is added to the beginning of the packet as the traffic goes from here. When the packet reaches switch 2, it understands that it is VLAN 10 and transmits it to the users in VLAN 10. In the same way, if the users in VLAN 20 want to access the users in VLAN 20, more than one VLAN traffic can pass from one port of the switch to the other port by adding a VLAN tag to the beginning of the packet they send, but normally the ports to which we connect end users or access ports are only one VLAN to these access ports, but more than one VLAN can pass through the trunk port. Let's talk a little bit about frame tagging on this page. As you can see here, it has an Ethernet frame. At the end of this frame there are FCS, data, type, source MAC address, destination MAC address fields. As you can see here, the 802.1q tag is added to our frame. This protocol is the trunking protocol that IEEE has created. There is also InterSwitch Link ISL, which is a protocol that Cisco has created and is specific to Cisco. It only works on Cisco devices. But the 802.1q trunking protocol created by IEEE supports this protocol in all switches in brands such as HP, Aruba, Juniper. In the Ethernet frame packet we send, the VLAN goes through our information, where information such as our VLAN ID, VLAN type and priority is added to our frame packet with the 802.1q trunking protocol and reaches the port where it will go. On this page, let's talk about data forwarding between VLANs. As we mentioned before, when we divide our network with VLANs on a switch, if there is no router or layer 3 switch in between, these VLANs cannot communicate with each other. The broadcast domain of this is separate. Our users here need a layer 3 device or a router if they want to access the users here. As you can see in the figure here, we have divided our switch into VLAN 10 and VLAN 20. So that the users in the red network here can access the blue network, we put a router in between and connect the fast Ethernet 0 port to the VLAN 10 port of the switch, and the users in the VLAN 10 access the router from the fast Ethernet 0/0 port. In the same way that we connect the fast Ethernet 0/1 port to the switch's port, which is VLAN 20, and make it accessible to the users in the VLAN 20. We give the users here the IP of our router. Let's say it's 192.168.20.1, let's say it's 192.168.10.1. When users on VLAN 20 want to go to the 192.168.10.0 network, they first come to the router and ask the best way to go to 192.168.10.5, look at the router routing table and forward the packet from fast Ethernet 0/0 to Dino, but if there is no router once in a while, you will not be able to do data forwarding between VLANs. We need a layer 3 device to make data for warning between VLANs. This switch may have a layer 3 feature on it. If it has a layer 3 feature, we can also forward data to the switch without the need for a router. On this page, let's look at the VLAN trunk configuration. We will process it in detail when making a lab. We make a lab just like here and we see how the VLAN traffic between switch 1 and switch 2 is done together when we are doing lab. Let's talk about data and voice VLAN on this page. There were classic telephone exchanges in our companies before and we used to use the telephone cables by pulling them to our tables. Computers used to connect them to the switch with Cat5 or Cat6 cables, but now there are phones that work over the network we call IP phones, and we use the phones that work over this network by connecting them to the switch. As you can see in the figure here, a cable from the switch comes to our phone. There is a mini switch with 2 port inputs on the back of our phone. We enter the cable from the switch into our phone, and we plug the cable from our phone into our computer. So what's the advantage of this? We can use both our phone and our computer by pulling a single cable, and in this switch, as I said before, we can only assign one VLAN to a port of a switch, but there is an exception. If you are using an IP phone, you can assign 2 VLANs to that port. One will be a data VLAN and the other will be a voice VLAN. For example, let's say voice VLAN 20. If the VLAN is also 10, you can assign 2 VLANs this way, but if you specify that it is only voice, otherwise you can assign only one. We can also configure data and voice VLAN in this way. We will do these examples together with you when we make lab. In this way, our cable comes from the switch and here it goes into the phone. We set this place as VLAN 11, we make this place VLAN 10. That's all we have to say in this lesson, so goodbye to see you in our next lesson. Hello everyone, we will do a sample lab study for VLAN configuration and verification in this lesson. I have already prepared the file that we will use in the lab and added it to the bottom of this video. After you download this file, you can open this file by saying open from the file section and you can do it with me. Now let's first look at our topology. We will create 2 VLANs in our topology. Our first VLAN is VLAN 10, our second VLAN is VLAN 20. I called this the accounting VLAN, I called it the RAND VLAN. In the VLAN here, we will use the 192.168.10.0 subnet, and in our VLAN here, we will use the 192.168.20.0 subnet. Our computer here is 10.1, this is 10.2, this is 20.1 and 20.2. Now let's connect to our switch and start configuring our VLANs. Let's go to enable mode by typing enable immediately. I enter global config mode by typing CONFT. I write VLAN and put a question mark. As you can see here it shows that we can create between 1 and 4.094 VLANs. If we use the ISL protocol we can use it from 1 to 1005. Our VLAN ID is 10, let's name it and write our name with the name command. Let's exit, let's say VLAN 20, let's get RAND in VLAN 20. We didn't write a name, let our name be RAND. Let's call it exit. After creating our VLANs, we need to assign these VLANs to our ports. Let's look at our ports, Fast Ethernet 0/1 and 0/2 in VLAN 10, Fast Ethernet 0/3 and 0/4 in VLAN 20, let's configure them immediately. Our command is interface fast Ethernet 0/1. First we select the mode of our port, I type switch port mode and press the question mark. Our options here are access, dynamic and trunk. We talked about trunk and access mode, but we didn't talk about dynamics. Normally our ports are in default and dynamic mode. What does this mean? When we connect two switches together, the ports of these two switches will be access ports if they are in dynamic mode, but if you leave one side of the switches in dynamic and make one side a trunk, the other side will automatically be a trunk. If you access one port and the other side remains in dynamic, there will be access ports on both ports. You can manually trunk on both sides or you can make access on both sides. Here we select the manual mode, indicating that this port of the switch is the access port. After selecting the mode we will also choose which VLAN to assign. I write switch port access VLAN 10. Now let's say exit and make our second port. Let's choose our mode first and then assign our VLAN. Now I say exit. Let's make our third and fourth ports at once using the range command we learned before. Fast Ethernet we configured 0/1 and 0/2 separately, but now let's configure 3 and 4 at once. I write interface range fast Ethernet 0/3-4. We will configure 3 and 4 at the same time. Let's choose our mode first. Let's say switch port mode access, and then let's assign our VLANs. Switch port access VLAN 20. Now I say end. Let's verify the configuration we made with show run. As you can see here, fast Ethernet 0/1, fast Ethernet 0/2 on VLAN 10 and in the mode of access. In our ports 3 and 4 here, we entered VLAN 20 using the range command at once. Now let's continue below. We can also see our VLANs with the show VLAN brief command. Show VLAN, let's put a question mark. Here there are ID, name and brief options. When we write a brief it shows us all the VLANs. As you can see here, our VLANs also have a name, VLAN 10, their name is accounting, VLAN 20 and their name is RAN D. VLANs between 1002 and 1005 are specially reserved and you cannot use these VLANs. Here it also shows our ports. We can see that VLAN 10 is assigned to fast Ethernet 0/1 and 0/2, fast Ethernet 0/3 and 0/4 are assigned to VLAN 20. Let's look at another of our commands, type show VLAN ID 10. With this command you can also see the VLAN 10 information, the name of which is accounting, it is active and fast Ethernet 0/1 and 0/2 ports use this VLAN here. After assigning VLANs, we're done here and let's come back to our topology. Here we have created VLANs through the switch or assigned VLANs to our ports. Now let's give IP to our computers and check if they communicate with each other. I'm coming to PC 0. Here I come to desktop and click on IP configuration. Our IP address is 192.168.10.1. When I click on subnet mask, it comes by default. Now I come to PC1. On PC1 I also come to IP configuration under desktop. Here at the IP address 10.2. This place is also okay. Now let's make PC2. The IP of the PC2 is 20.1. I come to PC2 and configure the IP address. This is 192.168.20.1. Now let's make PC3. I come from desktop to IP configuration. This is 192.168.20.2. I do these IP configurations so that you can see them. I will set these IPs in advance in the labs from now on, because I will prepare them and put them under the video so that we do not waste time by doing them again and again, and you can download and use these files. For example, our current topic is VLAN configuration. We just need to enter our VLAN commands. We should not bother with configuring these IP addresses. These are a waste of time for us, so I will prepare the labs in advance and put them under the videos. If you want to do it manually, or you can download it from under the video and do it with me. Now let's get to PC0. PC0's IP is 192.168.10.1. From here let's ping 192.168.10.2. Let's get out of here and open command prompt. Let's ping. It needs to access 192.168.10.2 because it is on the same network. It is currently accessing 10.2. Now let's look at PC1. PC1 is also VLAN 10, so it needs to reach 10.1. Let's look at this. Let's get out of here and open the command prompt. Let's write ping 192.168.10.1. It's reaching here. Now let's try to access PC2 from this computer, that is, try to access the user on a different network. We will not be able to access it from here to there because its VLAN is different. If it does not have a default router, gateway, every once in a while, it cannot access it. We will also show you the default router when we do the lab for data forwarding between VLANs. Now let's come back to PC1 and ping PC2 from here. Let's write 20.1. As you can see, ping is not going because this host is on a different network. We need a gateway to go to this, and I will show this in our next lessons. That's all we will tell you in this lesson for now. Goodbye, to see you in our next lesson. Hello everyone, I will show you the VLAN trunking configuration in this lesson. In our topology, we have two VLANs, VLAN 10 and VLAN 20. VLAN 20 I named RAN D, and VLAN 10 I named it accounting. VLAN 10 will use the 10.0 subnet, VLAN 20 will use the 20.0 subnet. Here we have switch 1 and switch 2, we have 2 users on switch 1, we have 2 users on switch 2. In VLAN 10 we have a total of 4 users, 2 users here and 2 users here. In the same way, in VLAN 20, there are 2 users here. I have done IP configurations before. I have also done VLAN configurations. Since our subject is only VLAN trunking, I will show how to make VLAN trunk by doing VLAN trunking between these 2 switches. If you want to practice, you can create VLANs again. I have created VLANs on the switches right now. We will only see if this user can access the user on the other switch by doing VLAN trunking between the 2 switches right now. In the same way we will see if they can also access the user on this switch. First, let's check our settings on switch 1. Let's call it show run. As I said, if you want to practice, you can do them manually. Our ports 1 and 2 are in VLAN 10 and our 3rd and 4th ports are in VLAN 20. Here our ports 1 and 2 are on VLAN 10 and our ports 3 and 4 are on VLAN 20. You can download this lab with these settings set. In the same way all VLANs are assigned, VLAN 10, VLAN 10, VLAN 20, VLAN 20. As you can see here, switch 2 is okay. Gigabit 0/1 ports are connected between switch 1 and switch 2. Let's make this port a trunk so that the VLANs between these 2 switches can reach each other. I'm going to switch 1 first. I write CONFT. I write interface gigabit 0/1. Switch port mode, I put a question mark. We're going to do it to trunk, I say trunk. As you can see, its status has changed. Let's say exit immediately, I say end. Let's save the settings we made. Copy run startup, I write briefly. Now let's get to switch 2. Likewise on the switch 2, I press Q and say CONFT. Interface gigabit 0/1, I write the commands in abbreviated form. I write switch port mode trunk, I say end. I write copy run startup briefly. Let's check our settings by typing show run. As you can see, the gigabit 0/1 switch port mode trunk. Let's write a show VLAN brief. As you can see, fast Ethernet 1 and 2 are on VLAN 10, and ports 3 and 4 are on VLAN 20. Let's write a show VLAN brief on switch 1. Here we have a VLAN trunking configuration between the 2 switches at the moment. I created our VLANs before. If you want to practice it yourself, you can do it manually. I recommend you to practice a lot. I prepare the videos in advance so that they are not too long and do not get bored, so that our videos are short. Now let's do our tests. Let's go from PC0 to PC7 and ping from 10.1 to 10.4. I write ping 192.168.10.4. As you can see, although it is on different switch, I can access it. My users here have accessed it with the user here. Let's ping 20.4 and see if it can access. We can't access 20.4 because it's a different network. We need to do IP routing to access it, and I'll show you that later. That's all we're going to do in this lesson for now, so goodbye, to see you in our next lesson. Hello everyone, I will show you the voice VLAN configuration in this lesson. Since this lab is short, I did not prepare it in advance and add it to the bottom of the video. Let's do it together. Let's come to network devices. Let's pick one switch here. Let's put the switch here. Let's come to the end user devices and choose IP phone. Let's put a computer in. Now let's connect the cables of these. We use flat cable. From here we choose the switch. From here we select the PC port and connect it to our PC. In default, our phone does not work because the adapter is not plugged in, so let's click on the phone and plug in the adapter. We take the adapter from here and plug it in here and our device works. As you can see, all our ports have turned green. Now let's adjust the settings. I click on switch 1 and open command line interface. Let VLAN 10 be called data. Let VLAN 20 be called voice. I'm exiting. Let's go to our port. Our phone is connected to Fast Ethernet 0/1. I write interface Fast Ethernet 0/1. First we write switch port mode access. Then we select our voice or data VLAN. Let's select our access VLAN first. Our access VLAN is 10. We will use it for data. We write switch port and then we write voice instead of access here. We write voice VLAN 20. As you can see, I was able to assign 2 VLANs under one port. We need to use it as voice so that we can assign 2 VLANs under one port, otherwise we will not be able to assign 2 VLANs. Let's save our settings by typing end. I write copy run sta in short. Let's write show run and look at our settings. As you can see, our configuration is as simple as that. All we have to do is type switch port access VLAN 10 and switch port voice VLAN 20. Let's check with the show VLAN brief. As you can see here, VLAN 10 is named in data and Fast Ethernet 0/1. Likewise, voice VLAN 20 is defined as Fast Ethernet 0/1. Since we use IP telephony in our network, we have separated our networks. Our phone and computer here can run in different subnets, so this is in the 192.168.10.0 network, while this is in the 192.168.20.0 network. Since there are VLANs in our network, we can use it in this way. If you do not have a VLAN structure in your network, if you are using a single VLAN, then you do not need to assign any VLAN to the port of the switch. Again, using a single cable, you can connect the incoming cable first to the phone and then from the phone to the computer. Then the IP of both the computer and the phone will be in the same subnet. This is how it happens if you do not configure VLANs, but we prefer to configure VLANs in our networks because there are various devices in our network such as IP cameras, access points, IP telephony and IPTV, and by separating these devices with VLANs, we are both grouping them and separating their traffic. This is how we configure data and voice VLAN. See you in our next lesson. Goodbye. Hello everyone, I will tell you about the spanning tree protocol in this lesson. I mentioned the spanning tree protocol before. The spanning tree protocol is a protocol that blocks looping between our switches. So why do we need the spanning tree? Why should there be a vicious circle in our network? As you can see in the figure here, when we physically connect our switches to each other in this way, as you can see here, vicious circles are formed. The spanning tree protocol was developed to prevent these vicious cycles. First let's take a look at the figure here and see what happens when the spanning tree is absent. The Bob user here sends a frame packet from here. The packet goes to switch 2, goes from switch 2 to switch 1, from switch 1 back to switch 3, from switch 3 back to switch 2, so the frame packet goes around our network and enters an infinite loop. This causes unwanted traffic in our network and prevents our switches from working. The spanning tree protocol has been developed to prevent this. In our form here, the spanning tree protocol is active on all switches. Let's take a look at what is different here. We have made a cable connection from switch 3 to switch 1, and we have made a cable connection from switch 3 to switch 2. Here the packet Bob sends goes to switch 1, it reaches Larry on switch 1, and from there it goes to switch 2, but it can't come back to switch 3 from switch 2, because the port here becomes blocked because of SCP. If our cable here is disabled, the block here will automatically take off and our traffic will go from here to here. In this way, spanning tree can prevent vicious cycles that may occur in our network. On this page, there are some terms that we use in spanning tree. Let's talk about those terms. Root bridge, bridge ID, BPDU, non-root bridges, port cost, root port, designated port, forwarding port and blocking port. This is our blocking port blocked. Forwarding port means it will transmit frames, while BPDU shares information between the switches with a received packet sent between our switches. If it is bridge ID, you may think of a switch when you say bridge because in the past, switches were called bridge, and this bridge ID is from there. Our switches have an ID number, which we call bridge ID. The bridge ID default is also 32,768, which are used to determine root bridge. If you pull a switch's bridge ID to less than 32,768, then that switch will be root bridge. When you leave the bridge ID of the switches in default, the The root bridge selection is made according to the MAC address. The switch with the MAC address is the root bridge. Let's look at the root switch selection on this page. Each switch has a priority value, switch ID, and bridge ID. If these IDs are equal on all switches, then the switch with the lower MAC address will determine itself as the root switch. As you can see here, switches send BPDU packets among themselves. These packets are sent every 2 seconds, and the switches share their MAC addresses and bridge IDs with each other. The switches here also look at their bridge ID and cost value. These cost values vary according to the type of interface you use. Each interface has its own cost value. According to these cost values, root bridge is selected. So let's look at why choosing root bridge is important. All ports on the switches become converged when they switch to forwarding or blocking mode, and no data is transmitted in the switch until the converge is completed, and not transmitting the data causes traffic interruption in our network. This converge time, that is, the time for the ports to switch to blocking or forwarding mode, takes about 50 seconds. To reduce this time, we need to determine our root switch. This process will be faster if the root switch is a powerful switch. Choices will be faster, such as which port will be block, which port will be in forwarding mode. To summarize, we need to choose a powerful switch when choosing the root switch to shorten our converge period. Let's take a look at the state of our ports here, where a non-root port also shows cost usage. When choosing our ports between switches, the speed of our ports is also important. These ports have default cost values. You can see these cost values in the table here. The cost value of a 10 megabit port is 2 million, and the cost value of a 1 gigabyte port is 20,000. According to these cost values of the interfaces, root port selection is made. You can see the selection of this in this way. The cost value between these two switches is 5. The cost value between these two switches is 8. The cost value between these two switches is 4. The ports of this switch are selected as the root port. The table here also has IEEE default values, which you can also change manually if you want. Let's look at the Rapid Spanning Tree Protocol on this page. Rapid Spanning Tree Protocol is a protocol developed because STP has vulnerabilities and deficiencies over time. It was created by IEEE with the protocol number 802.1W. Before this protocol was created, Cisco developed features such as port fast, uplink fast, and backbone fast to close the gaps of STP, and added it to its own iOS operating system, partially eliminating the shortcomings of STP. But since these features were exclusive to Cisco, other brands could not use it, so IEEE standardized RSTP and made it available to other brands. Let's take a look at the comparisons of RSTP and STP. RSTP and STP, they use the same boards when selecting root port, root switch, and designated port, but RSTP uses discarding instead of blocking. The table on the right also shows the status comparisons of RSTP and STP ports. RSTP, it adds a mechanism by which a switch can change the root port before switching to forwarding mode, in the same way that it adds a mechanism to determine the designated port before switching to forwarding mode. RSTP shortens waiting times in some cases. It works faster than STP. Let's talk about port fast, BPDU guard, and Ether channel on this page. First of all, let me tell you about port fast. If you remember, I mentioned the time it takes for switches to become converge. When you plug a device into the port of the switch, this port can be converged for about 50 seconds due to STP. If you need to get an IP from the DHCP server and you are sending a request to DHCP, the converge period here may cause your DHCP request to time out, so we can usually make the end user ports port fast so that these ports are converged faster. If you make a port of the switch port fast, you must also open BPDU guard on that port. What does BPDU guard do? When you open BPDU guard, BPDU packets do not come and go from that port, and you accidentally prevent a switch or hub from connecting to that port. In the figure here, you can see the example of Ether channel. We can connect it with two cables to have physical redundancy between these two switches. When one cable breaks, we configure the Ethernet channel to continue communication with the other cable. The difference of Ether channel from STP, if you remember in SCP, one of the ports here was blocked, but in Ether channel, one of the ports is not blocked. Here we have a 1 gigabyte connection, here we have a 1 gigabyte connection. We can also load balance by sending some of our data from this port and some of it from this port. Since we use two ports here, our total bandwidth is 2 gigabytes, but we do not send a 2 gigabytes data packet at a time. We only provide load balancing and redundancy. That's all I'm going to tell you in this lesson, so goodbye to see you in our next lesson. I talked about the spanning tree protocol in our previous lesson, and let's put into practice what we said about spanning tree in this lesson. Let's open Packet Tracer and come to Network Devices, select the switch and add two switches here. Let's connect them together by selecting the automatic cable. Since we connect the switches together, it needs to be converge. It takes around 50 seconds to be converge. Currently, BPDU packets are going back and forth between the switches and they are transmitting their MAC addresses, bridge IDs to each other with these BPDU packets. In a moment, one of the ports will be blocked, one of the switches will choose itself as the root switch, one of the ports will be the root port, one of the other ports will be blocked, and the others will be designated port. It takes about 50 seconds for the port to sit down, then connect to the switches and let's see. Now as you can see, switch 0 became a root switch, our switch 1 here couldn't be root, this was root, and a port of this was blocked, as you can see. The mechanism that prevents this loop is the spanning tree protocol. Now let's click on switch 1. Let's come to CLI on switch 1 and let's say enable. I'm writing show spanning tree. When we type show spanning tree, it shows the bridge ID of the switch and the MAC of the switch to which we are currently connected. Here it shows the ID of the root switch on the top side. Here the root ID and bridge ID are the same, because since this switch is a root switch, here it shows its MAC address in the root ID section. A little later when we look at the switch 1 we will see the MAC of this switch in the root ID section. Here you can see that this switch is root bridge and here you can also see its bridge ID. You can see here that both of the ports are designated ports. Now let's look at the other switch. Let's write enable. Let's write show spanning tree. When you type show spanning tree, it shows its MAC here as bridge ID and MAC of root switch is root ID. Here the priority is 32,769, and the default is 32,768, but you will say where did 1 here come from? 1 here comes from VLAN 1, since this is VLAN 1, the priority is 32,769, if this was VLAN 2, this value would be 32,770. The priority value increases because it adds the VLAN number here. If this was VLAN 10, it would be 32,778. As you can see here, Fast Ethernet 0/1 is the root port, that is, the port connected to the root switch, while the other Fast Ethernet 0/2 is waiting as an alternative port. As soon as our cable here is broken, this port will be opened and the traffic will pass. Now let's change our root switch by playing with the priority values. This switch is root switch because the MAC of this switch is low at the moment. Let's change the priority value of switch 1 to make it root. I go to switch 1, I switch to global config mode by typing conft. I write spanning tree and put a question mark. Here we will select VLAN. I write 1 and put a question mark. Here we can make this switch root switch by entering the priority value, or we can use the root primary command. Let me show you how we can do it. Let's write root and put a question mark. Here we see that there are primary and secondary options. You can root a switch with these commands. Let's change the priority value. You can't write the priority value here randomly. You need to write it as a multiple of 4096. Let's specify the priority value of this as 4096. Now let's write end and save the settings we made. Let's write show spanning tree. As you can see, this switch is now a root switch. Let's look at our topology. Now the devices are trying to be converge again, so right now it's showing both ports as block. Now I'm going to reload this switch. It takes about 45 to 50 seconds to converge, but when you press the button here, the process speeds up. As you can see now, it became converge and a port of switch 0 was blocked. Let's look at switch 1. Let's write enable. Let's write show spanning tree. Now as you can see, this switch has become a root switch. You can see the bridge ID and the status of the ports here. Now let's go to switch 0. Let's write show spanning tree. Of this switch, Fast Ethernet 0 to 1 became root, and Fast Ethernet 0/2 became an alternative block. Here it shows the ID and priority of the root switch is 4097. The information here is the information of the switch 1. It shows its MAC address and priority value here. We changed the priority value of switch 1 to make it a root switch. This is how you can choose spanning tree de root switch. Let's call it show run. Here you can see that the spanning tree mode is PVST. Let's take a look at these modes as well. Let's write spanning tree mode and put a question mark. There is PVST, rapid PVST, and a multi-spanning tree protocol here, which Packet Tracer does not support because it does not come out here. This is what you do to choose the rapid spanning tree protocol. before I do that, let's take a look at the spanning tree. I exit. Let's right show spanning tree. By default here you can see that the spanning tree protocol is enabled and writes IEEE, where IEEE is written STP is in operation. Now let's deploy RSTP. I am writing spanning tree mode rapid PVST. This is a protocol developed by Cisco, which I will tell you in our next lesson. When I talk about MST in our next lesson, I'm going to talk about this peer VLAN spanning tree. After entering, let's say end and check. When we type show spanning tree again here you can see that the spanning tree protocol is RSTP. This is the only command you need to enter to activate RSTP. In this lesson we made the spanning tree root switch selection and talked about spanning tree mods. That's all we're going to do in this lab for now. Goodbye, see you in our next lesson. Hello everyone, I will talk about multiple spanning tree in this lesson. We talked about the spanning tree protocol and the rapid spanning tree protocol before. Now let's look at the multiple spanning tree protocol. First STP, then RSTP, then MSTP were developed. Here too it shows the stages and years of development. STP in the 1990s, then peer VLAN spanning tree, PVST. It is a protocol developed by Cisco, which I will talk about a little later. Then rapid spanning tree was developed in the 2000s, and finally multiple spanning tree was developed. Now let's look at multiple spanning tree. In the 1990s, VLANs emerged with switches, and with the advent of VLANs, the existing spanning tree protocol was also developed, but we could apply spanning tree on only one VLAN. But in multiple spanning tree, we could select a root switch for each VLAN separately. We could select the port to be blocked separately. As you can see here, there is a VLAN 1 topology. Here we have a VLAN 2 topology. For VLAN 1 we say switch 1 is a root switch. For VLAN 2 we say root switch switch 2. We can choose this in the MST, but we cannot make this choice in the STP. For example, here at the multiple spanning tree for VLAN 1, the gigabit 0/2 port of the switch 3 is blocked, and in VLAN 2, as you can see, the switch 1 is not the root but the switch 2 root, and the ports here are designated port. The port here is the root port, here is the alternative block port. To summarize the multiple spanning tree, it supports multiple VLANs, so we can select different root switches for each VLAN and block different ports. Now let's look at the modes and standards of spanning tree, peer VLAN spanning tree. It is a protocol developed by Cisco to complete the shortcomings of spanning tree. Then, in 2001, when IEEE created RSTP, Cisco created the RVST Plus standard, which provided more features than RSTP while providing spanning tree per VLAN. Then, since IEEE did not fully adopt the PVST Plus and RPVST Plus developed by Cisco, it created a different protocol as MSTP, which it initially identified as 802.1q, but later changed the code of this protocol to 802.1s. In the table here you can see the names of the protocols: STP, PVST Plus, RSTP, Rapid PVST Plus and MSTP. We can only implement STP for a single network, but we can only apply PVST Plus for every VLAN. We also apply RSTP to only one VLAN, but we can apply Rapid PVST Plus for each VLAN, and in MST we can apply one or more. Here we also show the configuration parameter. When we did PVST, I showed how we commissioned Rapid PVST in our previous lab, but I could not show MST in Packet Tracer because MST does not support. There is no configuration of MST in the CCNA training curriculum anyway. This topic is included in CCNP Enterprise. MST is briefly by to see you in our next lesson. Hello everyone, in this lesson I will show you how to configure the Ether channel. I have already prepared the lab, put it under the video, you can download it from there. We have 3 switches in our topology, switch 1, switch 2 and switch 3. We will configure the yellow side with the port aggregation protocol developed by Cisco, and we will configure the green side with the link aggregation control protocol used by all brands that IEEE has standardized. Let this be channel group 2, and this is channel group 1. Cisco supports both of these protocols in its devices. Let's say our backbone switch is Cisco in our scenario here, switch 2 Cisco here, switch 3 is any brand. We will do our lab. I've removed the text here so that our lights look clear. This is Fast Ethernet 1 and 2, this is Fast Ethernet 3 to 4, this is Fast Ethernet 1 and 2, here is Fast Ethernet 1 and 2. Since spanning tree is now active, our port here and our port here have been blocked. We have 3 switches in the case study we have done here, and we will connect these switches to our backbone switch with 2 ports. When we make an Ether channel on these switches, spanning tree perceives the 2 connections here as if there is a single interface, and makes one of these ports a root port and a designated port, that is, it sends the frames by forwarding the 2 ports. When we make an Ether channel, these ports are also load balancing, because the spanning tree is currently active, one of the ports is blocked, traffic only goes back and forth from the port that is active here, but when we make an Ether channel, our two ports here will look like they are one port, and Ethernet frames can be moved from both ports. We'll also look at how it does load balancing at the end of our lab. Now let's turn on our switch 1. I'm writing enable CONFT. I will use the interface range command as we will enter the same commands in fast Ethernet 0 and 1. Let's look at the modes by typing channel group 1 mode and putting a question mark. When you select active mode, the link aggregation control protocol becomes the passive de-link aggregation protocol. We're going to make this place active, we're going to make this place desirable in port aggregation, we can make this place desirable and we can make this place auto. Here we need to make one side active, the other side can be passive or active, but surely one side will be active. In port aggregation, one side will definitely be desirable. We're doing the port aggregation side right now, let's make this place desirable. Let's make our ports 3 and 4 active, we will make this passive and this place auto. I say exit, I find the commands I entered before with the arrow keys of my computer and make the third and fourth interface settings by typing 3-4. I'm doing channel group 2 here. I also do active to our mode. I say end. Let's check our settings with show run. As you can see here, Fast Ethernet 3 and 4 are in active mode and group 2 as well. Fast Ethernet 0 and 1 are also in group 1 in desirable modes, where interface port channel 1 was automatically created when we entered the channel group 1 command under interface. Our traffic will now travel through this interface and spanning tree will see this interface as a single line. Let's check it out with show spanning tree. Right now it shows Fast Ethernet as 1, 2, 3 and 4, and when we do switch 2 a little later, it will be port channel. Now let's do the switch 2 and we'll look at it again later. Now let's do the switch 2. I write interface range Fast Ethernet 0/1-2. I'm doing channel group 1 mode auto here. Let's call it exit. Let's call it end. Now let's make the switch 3 and then let's see. Let's use the interface range command. Here I am doing channel group 2 mode passive. Now let's go to switch 1 and look at it again. Let's write show spanning tree here. At the moment, port channel 1 is okay, we will see it here when port channel 2 is ready in a moment. Let me speed up the process a little bit from here. Now all of our lights are all green and as you can see we don't have a blocked port. The spanning tree protocol sees our two connections here as a single connection and can forward from both ports by choosing one side as root and one side as designated port. Let's check this. As you can see, port channel 1 and port channel 2, for example, on the port channel 2 side, this port became root, and on the port channel 1 side, this port became the designated port. So this place became the root port, this place became the designated port. In this group, this is root, this is designated, in this group, this is designated, and this is the root port. Let's look at switch 2. I'm writing show spanning tree. This is the root port and it's in forwarding mode, so our frames are going. As you can see, spanning tree only sees port channel 1 here, it doesn't see interfaces anymore. He sees the switch 3 in the same way. Now that our Ether channel configuration is complete, let's take a look at the show Ether channel summary command. Here it shows group 1 and group 2. Group 1 uses port aggregation protocol in Fast Ethernet 0/1 and 2. Group 2 also shows the use of link aggregation protocol in Fast Ethernet ports 3 and 4. Now let's check both switch 2. I'm writing show Ether channel summary. Here we can see the port aggregation protocol. Let's look at switch 3. I'm writing show Ether channel summary. Here group 2 and port channel 2 are using link aggregation protocol. Here is the first and second port, and here is the third and fourth port. Now that our Ether channel configuration is complete, if you are not using multiple VLANs on our network, this is enough. but if you are using multiple VLANs on your network, you should also switch these ports to trunk mode. Let's check with the command show VLAN brief. As you can see here, port channel 1, port channel 2, fast Ethernet 1, 2, 3, 4, they are all under VLAN 1 right now, so all the ports on the switch are under VLAN 1. Now let's look at the trunk. I'm writing show interface trunk. It doesn't show because we don't have a trunk port. Let's call it show run. If you are going to use VLANs, you need to make the port channel 1 and 2 interfaces here trunks, and when we make them trunks, these interfaces will automatically switch to trunk mode, but in some iOS versions they may differ, so they may not pass automatically, so you control them. If they are not automatically trunked, you do them manually. I write CONFT, I switch to interface port channel 1. I make a switch port mode trunk and get out of here. I find the commands I entered with the arrow keys. I say port channel 2. I say switch port mode trunk and log out. When the port made a trunk under the channel interfaces, fast Ethernet 1, 2, 3, 4 was also a trunk. Now let's do the switch 2. INPA 1, which is the short spelling. Switch port mode trunk I write. Now let's do the switch 3 by saying end. Here is port channel 2. Switch port mode trunk, which is a short spelling of it. I say end. Let's write a show VLAN brief. Now that port channel 2 is fast Ethernet 0/1 and 0/2 trunks, it doesn't show up here. Let's look at it with show interface trunk. It now shows that port channel 2's mode is on and 802.1q trunking mode. Let's write show ether channel summary. Here you can also see the use of link aggregation protocol. Now let's look at switch 1. Let's call it a show VLAN brief. The port does not appear here anymore as channel 1, 2, and fast Ethernet are trunks from 1 to 4. Let's write show ether channel summary. It shows that the port channel interfaces are active and the protocol they use. Let's look at the show interface trunk command. It shows that port channel 1 and port channel 2 are in trunk mode. Now VLAN traffic can also pass between our switches. This is how we configure ether channel between two switches. If you are using VLAN, we make a trunk with the switch port mode trunk command. If you are using a single VLAN, you do not need to trunk the ports. Now, after configuring our ether channel, let's take a look at how load balancing is done. Let's check it on switch 1. When we write show ether channel load balance, our options come out here. In IPv4 and IPv6, it distributes load among the interfaces by load balancing according to the source MAC address of the outgoing packets. All switches default to load balancing based on their source MAC address, so let me show you how to change that. Let's write port channel load balance and put a question mark. When we put a question mark, we have options such as destination IP and MAC, source destination IP and MAC, IP source MAC. Let's make destination MAC as an example. Let's end and show ether channel. Let's check with load balance. Now that our load balance method has changed to destination MAC, you can change it as you like on all switches, and you can adjust the load balance settings in this way. You can also configure the ether channel this way. So goodbye to see you in our next lesson.